Okay, let's start with the second talk. So the second lecture is given by Peter Binev from University of South Carolina about optimal recovery. Please go ahead.
Thank you very much. I want to thank the organizers. It's a very nice program. And also say about my collaborators, Andrea Bonito, Ron DeVore, and Gergana Petrova. They're from Texas A&M. Albert Cohen is from the Sorbonne in Paris, and Logan Dowen is from the University of South Carolina. So this is, so what is the problem? The problem we consider is something about PDEs for which we don't have complete information. So we can choose different things we don't know, but we emphasize now on the problem when we don't have information about the boundary, because this is a problem that often appear in different practical settings, in particular for in fluid dynamics. And then when we have incomplete information, usually we have infinite dimensional set of possible solutions, and we want to restrict that using some data. So the problem is to use this data to have a better understanding of what could be the solution. And of course, we want to take a fruit fly for our first experiments. So that is, we are taking elliptic boundary value problem, and we assume that we don't know the boundary. So we have considered different problems. I consider here that we don't know exactly what is the boundary conditions, but sometimes we can kind of split the boundary, especially if we have a domain with the internal and external boundary, and we can assume that we don't know one of them and do something about it. So, and the basic question is, what is the optimal accuracy to which we can recover the solution, and what is the near-optimal numerical algorithm to approximate this solution. So, the problem is the classical one for which we know that almost everything theoretically. So to solve, sorry, oops. Okay. To solve this equation, we have two main functions we need to know. This is the f and the g, and we have a Lax-Milgram theorem which actually connects the knowledge about f and about g with the norm of the solution, and we have to use the norm, so the solution usually is considered in H1. The f, the right-hand side, is considered in H-1, and the boundary is considered in H1 half. So then the problem for numerical recovery of U, we don't have enough knowledge if we don't know the boundary G to recover the function. So what we assume it is that the G belongs to a known compact set, which we usually have some unit ball in H1 half gamma, and then we actually want to describe our knowledge through this compact set. So in fact, when we have the model problem now, is that we have that the boundary conditions about G is actually given through this compact set, and then we can define another compact set, which is the compact set of the solutions, which solve the equation for any given G of this K on the boundary. In order to reduce, so usually K might have a very big radius, so that could be a very big set, and in order to reduce the radius of this set, we have to consider some data observations, which could be very large amount about this solution. And classically, people consider point evaluations of the function, but we want to consider linear functionals because that is much easier to formulate, especially if they are they're well known, and because they they are in the space of the linear functionals over the space of solutions. So we consider these linear functionals known, and but of course the data observations are unknown to us at the beginning. When we have them, we can eventually consider what could be the functions U which satisfies that. So the total information, we assume that we have a vector of linear functionals, and then also that we have the information about the values of this linear functional for the solution, and then we can define a smaller compact set than the original set K here, which is KW, which is all the elements of K which satisfy the data. So based, so what is the new optimal recovery? So our goal is to find, our goal is to find numerically a solution which is from H1 omega, that is the natural space for the solutions, which approximates simultaneously all the U's which could be from this set KW. So in order to do that, the easiest way to do that is to just define what is the Chebyshev ball. This is the smallest ball at H1 omega, which contains KW, and then the radius of this ball, which is called Chebyshev radius, could give us what is the error of approximation, which is the best possible error there. And then the Chebyshev center could give us what is the solution. In general, this might be not unique, the Chebyshev center, but we consider Hilbert spaces, so in this case it's unique, so no problems with that. So what we want to have, so the ball is unique in H1 omega, as I said, because it's a Hilbert space, and we have the optimal recovery is the radius, and then this is the optimal error. And what we have, we want to find a solution now, which is an optimal recovery of U, which is this center, but of course, when numerically solving the problem, we'll receive a different solution. So we will receive a different number, which is not the center. But we want different functions, which is not the center of that, but we want that it is constant times the radius, so constant times the optimal result. Keep in mind that the usual algorithms, we receive that for some epsilon, and this epsilon could be made sufficiently small, but we have to make sure that this is smaller, this quantity. So the basic numerical consideration in order to have neo-optimal recovery is to make the algorithm efficient enough so that when we make epsilon to be of nearly the same as the radius or constant times the radius, then the numerical computations would not be too bad. So that is practically what is the difficulty in the problem when we define the neo-optimal recovery, because in this case we have to meticulously see what are the errors which will make at each numerical step, so to guarantee what is happening at the end. So first of all, some people say, okay, why did you consider even this function f? Because it only pollutes the problem. Actually, this pollution is very interesting because what is happening, so if we consider the problem with the zero boundary conditions, that will give us some u0, and then we can say that actually u is the solution of u0, and uh, which is a harmonic function, which has a boundary value g equals the trace of the which is the harmonic function. So that is kind of an easy way out, and we want to define. So we're following this way, but we want to define the space HS. Here, the smoothness index S is actually connected with the smoothness on the boundary. It's not connected with the smoothness of the solution U. So that sometimes it's confusing when one formulates, but when it is a curly H, S would be the smoothness on the boundary, which is 1/2 less than what we have if we consider the smoothness on the whole domain. So this HS omega and with the curly H has nothing to do with HS with the straight H because of that. So what we do, we will consider first of all we have a problem because there are several equivalent definitions of the norm on the gamma, HS norm on the gamma, because we can use the trace norm, we can use the direct definition of the norm, and it depends on the boundary whether they are all equivalent or not. I'll consider that on the next slide. And then the good thing is about H. S is Hilbert space that's compactly embedded in H1, and therefore we have compact because we have a compact embedding of HS for S bigger than 1/2, and we have this inequality between the norms. Okay, so if we want to recover the harmonic functions, first of all, we have to start with we first want to consider the problem when KH is the unit ball of HS for some S, and that would be our compact set which we consider. So let me remind you that here we have that this is the ball on the gamma. Now we have to consider the other one, which is this curly H on the omega, and then we consider the norm of this space. So we have to define that norm, of course. And then what we have that our solution is from this U0 and UH, where we, of course, should have different data, because when we find the U0 solution, it could have some different values of the lambda functionals, which we say this W prime, and this W prime actually is okay. The lambda U0, and then the W prime would be the new data for which we have to solve the harmonic function recovery. Unfortunately, this is a numerical computations, and we cannot find omega W prime exactly. So that means we have to work on that. We have to estimate what is the error and to have the precise reformulation. So that means also we have that this radius is equal to that radius, but we have to add additionally some fuzziness, so to say, for this W prime. So the optimal error of recovery of U is the same as this one in the H1 norm, and the harmonic recovery problem does not involve F except for this W prime, which, as I said, we have to take care of it. So because we know W with certain accuracy only. So we can view the harmonic reformulation as an optimal recovery problem with perturbed observations. So now recovery of the harmonic. I want to say something about the Chebyshev radius, because usually this is a very complicated problem when we have Banach spaces, but in fact when we have a Hilbert space and centrally symmetric sets like the unit ball, then we have this minimal norm interpolant for the vectors of observations, and therefore we can consider so that the recovery in this case gives us that the Chebyshev center of KW is exactly the minimal norm interpolant defined here, which means that if we know exactly, we can calculate exactly what is this minimum, we'll have the optimal recovery with C equals 1. And the interesting fact about this is that this optimal recovery doesn't depend on X. Keep in mind that we want to measure in the norm of X what is the best approximation. However, the solution is something which is independent of X. That's something we can use. Of course, the radius would be different. It will depend on how we define the norm. Okay, so what are the difficulties? I want to say this is a standard problem. There is nothing that is kind of unknown about it because people did a lot of theorems about Chebyshev radius and approximation. The solutions of the differential equations are very clear. However, when starting to write what our algorithm is, because we want to firmly control the error for each step, we certainly found out that the literature about the solutions, about the norms, the equivalence of the norms is not complete. At least we didn't have a good references for some of the things which I think everybody studied in graduate school, but they are not very well written. So one has to be careful when citing that. So I'm just giving the two norms. So one of the difficulties is that in HS gamma, we can define the norms in two different ways, as a trace norm and as an intrinsic norm. The intrinsic norm is simply by using one of these formulas depending on how big S is. And then we are interested when we have equivalence of this norm. So, and they depend on the smoothness of the gamma. And if we have, so there is an easy example which shows that we can have a very smooth function, which, however, if we consider the polygonal domain of R2, then we have jump discontinuities of the gradient of the restrictions on the gamma. And that actually it doesn't belong to H1/2 on gamma, this gradient, which means that we should restrict S up to 3/2 if we want to have equivalence of the two definitions. So we do that in our studies. So it turns out that this in R2, if we consider a three-dimensional case, we also have the same bound. It's not the same in four-dimensional, of course, but anyway. So then we have to say something about the regularities of the function here. So we have this curly HS set, and we want to consider the classical Sobolev spaces. So in this case, we want to know for which R we have the embedding of HS into HR. And this is for R equals S plus 1/2 usually, but sometimes it's limited by some R star depending on the domain. No restrictions, of course, if we have a smooth domain. If the domain is just convex, we have R star equals 2, so the smoothness cannot be bigger than 2. And then if we have non-convex polygonal domain in R2 or a polyhedron in R3, then we have that R star is between 3/2 and 2, depending on the reentrant angles. Say in R2, this is the formula pi over omega, where omega is the largest inner angle. So if it approaches pi, then it would be actually if it approaches pi over 2, it would be that one. Let me see. No, okay. So, yep. So, the next thing is how we fit the data. Actually, that is the most important part of the research we did, because how to fit the data, we have to define, we know some functionals, lambda j, but we need to work with them, And the one way to work with them is to use the Ritz representers in HS. So if we assume that lambda j linear functionals over the HS, everything is fine, we could have the Ritz representers and want to find these functions. When we find them, we can define the Gramian matrix, which is from the scalar products between two representers, and then eventually solve the system with this as a main matrix. So we also have to approximate what is W prime, which actually makes the we have to use the calculation of the solution U0. So then, if A star is the solution of this system, then easily that would be our solution at the end. So that is the way to solve the minimum norm interpolant and find the solution. So now the problem becomes how we can calculate this A star and what would be the algorithm to find this solution. So of course we first have to find these Ritz representers and then have to solve the system. So we have first of all we have that U and UH star, which is the optimal recovery of the functionals, and we have that this is smaller than the radius of this space in H1. And as I said, we are measuring in H1, and that means it's different for different spaces, not in this HS. And that is the optimal recovery once we find this UH star would be U star, which is UH star plus U0, and then we'll have this general estimate about the functional. So the idea, of course, is to find some approximation of this U star, because this is ideal. We will not be able to approximate it, and to have this epsilon, and then to compare this epsilon to see when this is of the same magnitude as the Chebyshev radius in this space. Okay. So how we do the numerical recovery? We just have that. We first have to approximate the U0. We have to have that the linear functionals are continuous over H1 omega. And in that case, we assume that lambda is the maximum norm of these functionals. Then in order to write the solutions, we have to consider that for the data, we have to use the weighted L2 norm, not the classical E2 norm. And then we can write that using this constant lambda, the norm of the functionals lambda as a vector is less or equal to lambda times the solution. So using that, we can formulate the algorithm. So the algorithm, as I said already, we have to approximate first the U0 solution. So we have to find some epsilon 1, which is the error, and have to drive it below this error. Then we have the global estimates for the discrepancy of the global error of the approximate solution here is lambda s plus lambda epsilon 1, and the discrepancy would be lambda epsilon 1 between the two at most. In the second step, we have to find these linear functionals, and we have another epsilon 2, which is involved there in calculations of all these linear functionals. And then after calculating them, we have to compute the matrix G hat and its inverse. So in order to compute the matrix, we have to, we first have to consider what are this epsilon 2, and then have the estimate for the entries of the matrix. We use L1 norm, the matrices from L1 to L1 to estimate what is the error between the two matrices. And then in the last step, once we have, no, this is not the last step. This is still when we have the matrix G, we have it to some extent, and then we want to find the inverse of this matrix. And for the inverse, we calculate the number M, which is the what is the norm of the inverse, L1 norm of the inverse, and then L1 norm of the approximate inverse. And we have some inequalities between these norms, which involve the one for M involves M hat, and the one for for M hat involves M, and of course the other parameters are M. This is the number of solutions, the lambda and the epsilon 2. So we have to make sure that these numbers are smaller than 1, which we can choose small enough epsilon, and then we define this to be our delta, and we can make it arbitrarily small with epsilon 2. So after making this second step, the fourth step is very easy. Once we have the inverse matrix of G hat, we can calculate what is the solution A simply by solving a system. And the major advantage of this algorithm is that the first 3 steps can be computed without knowing what the data is, and that's why we can compute it for several different elements of the data. I don't have much time, so I'll try to say something about so first we have the theorem, and the theorem says that if we have chosen this epsilon and 1 and epsilon 2 small enough, we can make this whole quantities less than epsilon. This is a sign accuracy, and eventually prove this inequality, which means that for any epsilon, we can make it near optimal recovery for any constant c bigger than 1. So what are the, we can do the same for point evaluation data. Point evaluations, the bad thing about them is there might not be even linear functionals in the considered space H1. So that's why we have to do an extra step, and but we can consider that these functionals are anyway. We have to make a data evaluation. So if we are able to evaluate, then for this compact set, we assume that the solution is in the compact set K. We can assume that it is in a space for all the elements in this compact set. We have that the point evaluations are defined, and then go and modify the steps, including additionally, not only that the norm in H1 is smaller than epsilon. Keep in mind that the compact set is much smaller than H1. So when we calculate the H1 norm, we don't actually consider what is the error in the functional. So we have to add this additional condition. Same thing for the epsilon 2. When we calculate the evaluations of the functionals, we have to make this additional condition, and then we can prove the same theorem and have the same estimate. And at the end, I want to say some words about how we calculate the Ritz representers, because this is probably the most interesting part of it. So the Ritz representers, we can calculate them in two different ways. We can calculate them as a Galerkin solution of a differential equation, but we also can do it as using some a different formulation. So in a sense, to decrease the number of computations. So in order to do that, we have to go to the to define what is the restriction, the operator E, which is the harmonic extension operator. And when we have it, we can actually have that characterize the trace of the operator through this extension operator. Okay, so first the Galerkin formulation. We basically solving equation which satisfies this condition, that is the discrete harmonicity of the function, and when we do that, we solve the problem completely, and this is a good solution. However, it's not very good numerically. So in order to do a good, so we can solve that equations I have, but we can do the saddle point formulation, in which we just add additional unknowns and solve the system of equations. And in this way, we find a solution which is equivalent. However, the number of computations usually for the Galerkin solution is n to 1 plus d minus 1 over d, while here is just n in the saddle point formulation that gives a better solution. So, and at the end, I want to say something about the relation to deep neural networks, not that because they become very popular. And so what part of this problem, which is a data problem, and several people might consider it. So first, the computation of Ritz representers using finite elements in a saddle point formulation, it's still O of n computations. So in some cases, you might think that you can train a deep neural network to find a similar approximation of that with a faster algorithm. The second thing is the process of obtaining U hat H. This solution, we went through calculating all these phi j hat, which are the Ritz representers, and they could be a lot of them. They could be, because m could be a very large number, so we could have a lot of data. It eventually, if we do that with deep neural network, eventually we could have a better solution, faster solution, maybe not better, but anyway. And that is all. Thank you very much.
Thank you for your lecture. Are there questions?
So you compute these representatives.
Yep.
For the Hilbert space of harmonic functions, is it correct?
Yes, that is for, but we have to compute them numerically.
Yeah, but harmonic functions, this set is a reproducible kernel of Hilbert space.
Yes.
Can you use? Did you look for reproducible kernel? Because if you have a reproducible kernel,
okay,
then these representatives are given trivial by applying the functionals to the argument of the reproducible kernel.
Yeah, but you have to know the functionals.
Yeah, and so for harmonic functions on the ball, the non-explicit.
Yeah, but if this is not on the ball, if it is in the general domain.
But when you restrict the reproducible kernel, if you restrict to a subspace,
yeah, then you have to do numerical approximation.
Sorry?
You have to do numerical approximation.
No, you just restrict it. It does not change. It's arranged, the classic reproducible kernels. You don't need to change it, just restrict. So you didn't look at it.
Maybe you should continue
no, that is
in the coffee break.
okay.
We
consider that it is a possible solution, but it's impractical because of the numerical calculations, how you calculate the harmonic functions. Okay, we consider that.
Is there another short question, maybe? So if not, then thank you again.